Hello and welcome to our introduction to the next topic in our statistical inference and methods series. Today we're going to talk about analysis of variance. Now I'll start by saying if through this, which is just our introduction, you don't have 100% grasp of how to follow this method, that's totally normal, totally fine. As you work through examples in more detail and do it systematically by yourself, it'll become more clear. This is just our introduction to get an idea of how is this the same, how is this different, and why does this even exist? So if you think back, let's say here previously, we had our t-test for independent means, so to speak, where we had independent groups, two independent groups, and we were testing the null hypothesis if the means are the same or not. So here our research hypothesis was not the same. And we had our t-test, we set it up, we calculated the t-score, and everything made sense. The only real thing we're doing here is noticing that this t-test was for two groups and comparing two means. I could have more groups. I could have 3, 4, 5 groups independent that I'm testing to see if they are statistically the same, or if they, by way of their means, are significantly different from each other. So the analysis of variance steps in when I have more than two groups. It overlaps the previous t-test, and I can do it for two groups. Then the results will be identical. It's just I don't necessarily need to. The t-test is arguably a little simpler. So they do have an overlap in the two-group case. And then if I have more than two groups, then analysis of variance is the method that takes over. So the interesting thing here is that we're not going to test and work with means in the same way. Ironically, how we are going to try and figure out if the means are the same or not is by looking at the variance instead. But our null hypothesis is the same. It's just an extension of the previous independent means t-test, where we, under the null hypothesis, assume all the populations, all the groups are identical. Now, there could be slight variation in the groups, of course, but they come from identical populations, and therefore their means are the same, the population means. And the research hypothesis then is that something is different. Could be that just a couple of them are different. Could be that they're all different. Because I have more groups, my null hypothesis, I'll write it over here, for let's say 3 groups will be that the 3 means from the 3 underlying populations are all the same. And then the research hypothesis will be that for 2 of them, they're not the same. Let's just say like this, it's not the null hypothesis. mu1 and mu2 could be the same, but not mu3. There is something among these groups or these populations that's not the same. So I don't necessarily want to say mu1 not equal to mu2, not equal to mu3. That's not quite true. I don't know where the inequality sits. It could be that these two are equal and mu1 is not. So I don't necessarily want to say that. It is the opposite. There is an inequality somewhere. But if you want to write it casually as not equal, not equal, not equal, just be aware that it doesn't mean they're all different. Just something is different. So that's the underlying idea and how we progress from the independent means to this ANOVA, short for analysis of variance method, and what it's trying to do. I think that's the first important thing to understand. What are we trying to do? Not how, but just why does this even exist? So we're going to have our groups here. Let me just see if I can erase this. Not erase this, just sort of, yeah, just erase this real quick. I need the space. I need some of this space. Thank you. And then I just want to make this smaller, like so. So we're gonna have our groups here. Groups. This is group 1, group 2, or sample. These are, of course, samples from their respective populations. Now, they're going to have their own variance inside that is hopefully a representative of the population variance, and same for this one, and same for this one. So within the groups, these are all going to come from the same population under the null hypothesis. So I can use all of these within group variation to estimate the population variance. But then also between these groups, there is variance that I can use. Now, in the null hypothesis, the variance between the groups, they all still come from the same population, so that would be the same. However, if they don't come from the same population, there is some extra variation between the groups because they come from different populations. That's going to add variance where if the null hypothesis is true, that variance wouldn't be there. So if the null hypothesis is true, then there's variation just naturally occurring when I take a sample within the groups and between the groups. They all come from the same population. But if the research hypothesis is true, and there is a difference in the underlying populations, yes, within the groups there will still be variation. That is captured when I look at the groups between each other. But there's also going to be a variation between the groups because they come from different populations. So this is going to be the key to how we approach this. That I'm going to compare the between variance estimate to the within variance estimate, and we'll get to how we're going to do that. And how we are going to compare them is by making this fraction, this ratio, and if they are the same, it should be very close to 1. We're never going to get perfect because we're taking samples from our population, right? But if the research hypothesis is true and there is a between group extra variation, then the numerator is going to be larger than the denominator in this fraction I create, and I'm going to get a ratio greater than 1. And we call this the F ratio. It's going to have its own distribution, cutoff score, and everything like we're used to. It's just not going to look exactly the same. Okay, so that's the basic idea. Let's get into some detail with a specific example. I'm just going to do it like this, just to hide a little bit. And again, we're going to sort of run through this, but understand that it's not going to enable you necessarily right away to do your own example in detail from scratch. We're building up, just introducing the idea. Then in a future video, we'll work through examples, and then you'll get a better idea. So I don't want to get caught up in the detail too much, just getting an idea and then going deeper in when we do the examples in a slow and steady methodical way. So let's look at this criminal record study example. So here we have three groups, and we rated the jurors' decisions based on information that they get, but different pieces of information. The first group got information that the defendant has a criminal record. The second group had information that the defendant has a clean record. And the third group got no information at all. We want to investigate if that information affects the juror's decision. So our null hypothesis is that the mean score or rating, however we are rating the jurors' decisions, the mean population, the population means are all the same, that the information doesn't affect these, and these populations are actually all the same. And the research hypothesis is that they have different means. See, we don't say they're all different. Something is different somewhere. It could be between any two of them, and it could be all three for sure. So before I go further in that slide, let's have a look for how we're going to calculate these things. Because remember, we want to calculate this ratio. So first of all, within. How am I going to use the groups and the samples that I have to calculate within each group what a good estimate for the underlying population variance? So we're going to calculate the population variance estimates based on each group. So that's our classic variance estimate. Degrees of freedom, one less than the sample size. So let's look at the detail here of what we got in our criminal record study. Don't want to show too much there. So we had our three groups: criminal record group, clean record group, and no information group. And the ratings are over here. So you calculate the deviation from the mean, square deviation, sum of the squares, divided by sample size minus 1 in the same way as always. So I got variance estimates from each group: 4.5, 5, and 6.5. How we then merge these together, because under the null hypothesis they all come from the same population, right? All the populations are the same, so therefore the variances should be the same. So I'm simply going to average these out, add up all the variances, and divide by how many groups there are to get a better estimate, because within each group there's going to be slight variations. I just took a sample of 5. Of course, these variance estimates won't be the same, but they all estimate the population variance. So let's merge them and get the best estimate we can. So I'll worry about the degrees of freedom within in a second. Right now I don't need that, but it's written there. So our best estimate for the population variance that we'll call the variance within is then 5.33, just an average of these guys. Okay, so that's summarized over here, not over there, over there. Jumping between pages here a little bit. All right, so that should be pretty straightforward if you're on top of everything that happened up to this point. Now we want to estimate or the variance in a different way by looking at the groups, sort of each group as a whole. And we're going to do that. We're going to call that the between groups variance estimate. So what I'm going to do is I'm going to just take the mean of each group. So here in the first group, I have a mean of 8, second group mean of 4, then a mean of 5. I'm going to take that and then calculate the mean of those means, and we call that the grand mean. Add up all the means, divide by the group's average of all the means. That's the average of the means, the grand mean. And then I'm just going to treat these samples as single scores by way of their sample means, M. So then I take the deviation, and then I take the square deviation, sum the squares, divide by 1 less than the number of scores I have for this sort of simplified group of groups. And I get a variance estimate by looking at this sort of at a zoomed out level. Each group has a single score, the sample mean for that group, and I calculate the variance based on that group, and I get 4.34. Now, naturally, these aren't going to be the same, but they might be very close because of natural variations, and the populations underlying these might still be the same. So just because the numbers aren't identical doesn't mean anything, of course. So I then just calculate my between variance estimate. Now here is a little catch perhaps that I just want to be aware of. This over here is a variance estimate for the distribution of means, right? Because I'm looking at means. This is a mean, this is a mean, this is a mean, and I'm looking at the sample of means. So what I'm really estimating here is the variance, but for the distribution of means. And that's not ultimately what I'm looking at. I'm interested in the population variance estimate. This is a population variance estimate. Whereas when I look at between the groups, it's a distribution of means variance estimate. So if you remember, what is the link between the variance of the distribution of means and the population variance? Remember, I just divide by the number of scores, or the sample size. So therefore, to now reverse this and get an estimate through by this way, for the population variance, I multiply that by n, the sample size. All right, so let's see how that is done here. So that's a little catch, I suppose, that if you're not aware, that we could easily fall into that trap. So my group size, and we're going to go under the assumption, to keep things simple, that all the groups have the same size, 5 in this case, is what I need to multiply by my between groups, by my variance estimate for the distribution of means to get the between groups estimate. And I get 21.7. So we were a little quick. We can't compare this 5.33 to 4.34, even though they look comparable. We have to, and I fell into that trap as well. We have to realize that this is not estimating the same distribution as this top one, and therefore we multiply it by the group size, the sample size, which is 5 in this case, to get this. And these numbers, let's put them in a box. These are the numbers that should be compared. Now, just because this looks much bigger than that doesn't mean how much bigger is big enough to qualify as being significantly different in terms of the underlying populations. That's why we have a distribution that we measure these against. So when we calculate the ratio here, the between estimate over the within estimate, we get our F score. Now this F score, this ratio, has a distribution called the F distribution, and it looks like this. It has its own tables and cutoffs. Here's an example of the table where now both the numerator and the denominator has degrees of freedom that I need to be aware of, and then within each I have the 3 common significance levels. So this table actually has a lot of dimensions, so they're just giving me the numbers that are used most of the time. So let's see what we get. So here is our F distribution. Now I think I have a picture of this. Let me just triple check. So if we look at, jumping between many slides here, over here I think is where I want to be, yeah. If we now look at the degrees of freedom first, I suppose. So the degrees of freedom for the between groups, that's the numerator degrees of freedom. And when you look at the table, it'll say here numerator degrees of freedom. I have 3 groups. That's the number of groups minus 1. So in this example, I'm going to be in the 2 column. For the denominator, the within groups, I did the denominator first because it was, I think, more understandable, easier to do. The within groups estimate has degrees of freedom simply adding up all the degrees of freedom of the individual groups. Each one 5 minus 1, so 4, 4, 4 for a 12. And because in my F ratio calculation, that is the denominator, the table says denominator degrees of freedom. So we're going to look at 12. Let's take an alpha of 0.5, and we see here that our cutoff score is 3.89. That we've listed over here, 3.89. So it is important to remember what are the degrees of freedom, because that affects where I look it up in the table. So if we look at, I think this is a good slide next. Over here, this is our situation. We had our different groups, some variation between them. Calculate the F score, F ratio, and we get a 4.07. But our cutoff is 3.89. And this then shows, if we choose an alpha of 5%, that but it is past the cutoff, showing that a ratio like that is unlikely to happen if the populations were identical as we assumed. The ratio is significantly high, meaning that, oopsie, where's my calculation? This one. Meaning that this between estimate is significantly bigger than the within estimate, and by way of this ratio, that's how we make that decision. So we can go back to our layout here. We calculated the within, the between, the F ratio, compare that to the cutoff. If it's greater, we reject the null hypothesis, the evidence suggests that the populations are not the same, and that means that information available to the jurors makes a difference in the ratings of guilt or whatever rating scale we used. So that's going to be the idea. I know it's a little overwhelming the first time perhaps you see it. And I have 4 slides that I jumped through because there are more calculations. Not super involved, but there are some things to be aware of. But a first example is not what I'm going to base my comfort level on. It'll take some time, and as we go through it with more examples, it'll become easier every time we do it. But I find value in just getting sort of the big picture and then reinforcing that with a second example. So let's see our second example here. Willingness to volunteer. So we are asking people or rating their willingness to volunteer for something depending on their situation when you ask them. So when you ask them if they're alone, when you ask them when they're with a best friend, or when you ask them in a larger group like a classroom. So these are the 3 populations, and we have a group of the same size for each of these. So our null hypothesis is that they're all the same, that the willingness to volunteer ratio is all the same, and who they're with doesn't affect it. And the research hypothesis is that it does. So let's just have an idea here of what the actual numbers is that we're working with. On the left here, the alone group, the friend group, and the class group. We calculate the mean for each. Same as always, we calculate the variance estimate for each, and then we're going to average that. Let me just see if that's done over here. So the degrees, so within groups, I do first degrees of freedom. Well, the degrees of freedom for each, we had 6 in a group, so 5, so 5, 5, 5, so 15 for the degrees of freedom within. So that's the first important thing. And then when I calculate my best attempt at a population variance is when I average all the individual variance estimates and I add them up, divided by 3, and there we go, 2.53. So that will be the denominator that goes in the bottom of my F ratio. Then we sort of zoom out. I imagine zooming out, and now each group is represented by a single number, its mean. And I take the mean of that, called the grand mean, and then I calculate the variance estimate that way. And I get the degrees of freedom, the group's sample size of this group minus 1. And I calculate the variance estimate in exactly the same way, but remember this is for a distribution of means, and this is a population estimate. So I can't quite compare them yet. I need to convert the distribution of means to its population estimate. Now this is a population estimate by multiplying by the group size, 6 in this case. So now I'm comparing this 2.53 with 14.04 by way of the F ratio. That has a distribution based on the degrees of freedom, 15 and 2. So let's just go through the highlights here. So F distribution with 2 and 15 degrees of freedom. I need to just make sure, where do I find this cutoff? 3.68 rather. So 2 and 15, I have it over here. Now, which one was which, you might ask? Well, the numerator is the between group, so that's the 2. And we said 15, right? 2 and 15 takes me to the next page. Alpha, 5%, so 3.68 is right there. Okay, so that's where we get 3.68. And then we compare our F ratio, 5.55, to the cutoff, 3.68. It is more, so therefore, this is very unlikely with a 5% chance to be happening if the populations were the same, and we take that as strong enough evidence to reject the null hypothesis. In support of the research hypothesis, the willingness to volunteer appears to be different under different social conditions, depending on who the person is with when you ask them. Now, again, I'll emphasize here, we don't know where the difference is. We are only saying that there is a difference. So that's very important to realize, that all we're saying is the evidence suggests that it is different somewhere. It might be that when you're alone or with your best friend, the difference is not significant. It could be best friend versus classroom is significant and alone significantly different, and alone versus classroom significantly different. It could be only one pair. I can make different pairs here, different comparisons, right? When I have 3 groups, I can make 3 different comparisons when I do them 2 by 2. All this is saying, sort of a macro level, is there a difference, yes or no? So, what did I just do? That was the previous slide. I'm sliding over here. Oh, that was our calculation slide. My tabs keep jumping. I have to do it like this, okay. So, in an attempt to find where is the pair that is actually different, there are technically 2 sides to this. One side is planning where you're going to look before you actually do anything. That's a subtle difference perhaps in the beginning. Versus finding with the F test, there is a difference with ANOVA, and then going to look. Now, I'm not going to delve into too much detail on how these are different, because in this introduction level, I don't think that's the thing to really focus on. The issue is identifying the pairs where, not that tab either. Where is my tab? That one. Where is the difference? To try and find that. One way or another, I'm going to have to test 2 at a time. Okay, so we have these planned contrasts where we just test 2 at a time. So we still have the within groups. That should actually be first. I'm going to do number 2 first. Within groups is exactly the same, because that is the best estimate of the overall variance that I have. And the between groups estimate, when I only test 2 groups at a time, only 2 groups, I'm only using the information from those 2. So the grand mean will be different using only those 2 sample means. And then I do everything the same, basic calculations to get an estimate. So this will be updated. This between groups estimate, if I only look at some groups and not all of it, I've done my F separate from that, it will reflect that more accurately, because I'm trying to compare specific groups to see where is the significant difference that I know exists. Then I calculate a new F ratio in the same way, The within estimate will always be the same. Between is what's different because I'm not looking at all the groups at once. And I compare that to my cutoff, same as before. So if we look at the criminal record study, if you remember, we had 3 groups. I'm not going to go back to that slide because I'm struggling to find the slides. We had 3 groups, and the jurors received different information. Some received nothing, and we wanted to see if it affects their judgment, their rating. And we found that yes, there is a difference. The evidence suggests there is a difference. We don't know where. So if we now compare just 2 of the groups, let's take the criminal record group and the no information group. And we suspect that that's where the difference is going to be. Let's now test that. So I'll just show the whole thing, and hopefully it doesn't overwhelm you. So within groups, I want to do that one first. Same as before. We could just take that from our previous calculation, no updating necessary there. But the between groups needs a little adjustment. I'm using only the means of the 2 groups being compared. So in that case, it was 8 and 5, so only 2 of them. For the grand mean, the number of groups now is 2 minus 1. Number of groups minus 1. 2 minus 1. I'm only using those to get the estimate of the distribution of means, which I then multiply there by the group size, which is 5, to get 22.5 that I compare with 5.33. The degrees of freedom also updates. That's the number of groups minus 1. This will be the same as this. Lots of circles here, sorry. And then we calculate our F-score, or F-ratio, as usual, between estimate over within estimate. Our cutoff isn't quite the same because our degrees of freedom is different. The numerator one is now 1 instead of the 2 because I only look at 2 groups and 2 minus 1 is 1. Previously I looked at 3 groups and 3 minus 1 was 2. So it's not quite the same cutoff either. I do compare these 2, and I see that the F ratio is not greater than my cutoff, and therefore I do not reject the null hypothesis. It's a new hypothesis test that these 2 means are the same, and the evidence isn't strong enough to suggest that they're different. So by delving deeper in and looking and trying to see if the difference that we know the evidence suggests is between these 2 groups, it is not between these 2 groups. Okay, so with these planned contrasts, we can sort of zoom in and focus on 2 groups at a time instead of the overall all groups that the original ANOVA F ratio test was trying to do. Okay, so that makes sense. That makes sense. But unfortunately, it's not quite that simple. Well, it is and it isn't. We just have to be careful in how we make our decisions. Remember that what alpha means. Alpha is the chance of, or the probability of, a type 1 error, right? When I look at all the groups, so it's the probability that I assume the null hypothesis is true, but let me rephrase that. It's the probability that I reject the null hypothesis, but it was actually true. So let's just casually say it's my chance of an error. It's my chance of making the wrong decision. The problem is that if I, let's say, have two planned contrasts that I'm checking, I'm testing repeatedly two groups at a time, right? Remember, because I have many combinations of where the difference could sit. It might not be, I looked at this one, for example, and it wasn't between those two groups. It's somewhere else. So most likely I will have multiple of these planned contrasts to test. Okay. So what happens if we use an alpha of, let's say, 5% for each of these tests? Remember what alpha means? It means that if the null hypothesis is true, we can phrase it in two ways. There's a 5% chance of making a mistake, or there's a 95% chance of making the correct decision. So let's instead focus on that. 95% chance to make correct decision. Okay, but now I have two of these. So for test 1, I have 95% confidence in my decision. Test 2 is also 95% confident. So what happens overall? Well, not to get into how probabilities work too much, I have to do the decimal version here. My chance of making a correct decision, chance of correct decision overall, not making a mistake, is going to be 0.95 times 0.95, because it's one test followed by the next, followed by the next. It has a multiplicative property. And I get 0.9025, which means I'm 90.25% confident that I am making the correct decision. 90.25% chance of not making an error somewhere in these tests. That means that my chance for making an error is now up to 9.75 of a type 1 error somewhere among these tests. So there is a real danger in taking the original alpha for repeated tests. And that is that my chance of making a mistake in a conclusion somewhere actually increases. Now, it's not quite additive. I don't add 5% plus 5% plus 5% every time, but it's very close, actually. So a rough rule of thumb could be, it's roughly 10%. In truth, it's a little less, but it's a good rule of thumb to go on. That it increases dramatically. So the true chance of making an error in a decision somewhere, in one or more decisions, is actually much higher. So what can we do to try and avoid this? Well, we have what we call the Bonferroni correction. And all we're going to do is we're going to take our original alpha and make it smaller when we do planned contrasts or planned comparisons. How much smaller? It depends how many we're doing. So let's have an example over there. Let's say we have a study with 5 planned comparisons and we have an original overall alpha of 5%. Then we divide it into 5 little pieces and we use an alpha of 1%. Now, yes, 1%. If we, for example, have a study with 3 comparisons and we use an alpha of 5%, we divide it by 3. 4 comparisons, we divide it by 4, and so on. Because we saw that it's almost additive. And with the Bonferroni correction, it's sort of overcompensating by a little bit, but it's best to be safe. Right? So the Bonferroni correction is one fairly simple way to not let my type 1 error get out of proportion big here without me necessarily realizing it. There's an adjustment needed to keep that error in check. Okay, so that is definitely the most important one for us, but I just want to go a little bit further so that you are aware. We could also test these comparisons after the fact. So we did our ANOVA. There is a significant difference somewhere. Where is it? Well, if you have no idea where to look, nothing that you planned, you're going to have to test all of them to find which pairs are different. And with too many tests, now in the case of 3 groups, it's not that bad, right? I only have 3 different combinations. 1 and 2, 2 and 3, or group 3, or group 1 and 3. Not too many. But if I start with many groups and I'm looking to find which pair has that significant difference, that's going to be a lot of tests potentially. It increases really quickly. Then, unfortunately, Bonferroni isn't ideal because the Bonferroni correction uses an alpha that is very small. For example, if I start out with 5%, let's suppose I start with alpha 5% and I have 10 tests. So that means I'm going to use an alpha for each of those tests that is 5% divided by 10, so that'll be 0.5%. And when I test these, it really pushes my cutoff very, very far to the right. And that cutoff becomes so extreme that I'm very unlikely to get any decision and find any difference because I've shifted that cutoff so far. This easy fix adjustment to avoid the type 1 error blowing up doesn't quite work as well when I have so many tests and I have to go look for any combination. So the alternative is the Shefei test, where I'm going to follow the same procedure. I pick 2 groups and I just focus on that for the between group estimate. Within group estimate is the same, just like before. I figure the F ratio, but this approach divides the F ratio by the degrees of freedom between, which is the total number of groups minus 1. So that if I calculate an F, it's just an alternative. I have 2 alternatives here. I have 2 options, basically. I can shift my cutoff line further to the right, or I can scale my F ratio that I calculate back. These 2 things need to be adjusted. So Bonferroni shifts the cutoff line to the right, but with many tests, it's a little too far for me to actually have a practical use for it. The Shefei test adjusts the F ratio in terms of how many groups I had to start with. So let's look at that. For example, if I compare the criminal record group with the no information group, then I follow the same procedure. I get an F ratio of 4.22. Instead of adjusting the alpha, I keep alpha at 0.05. I'm going to divide the calculated F ratio by 2, number of groups, minus 1, 3 minus 1, and scale that back to 2.11, and then use that with my normal cutoff to make a decision. So I have these two that I just want to be aware of. In our questions, we'll use Bonferroni more often because we don't have a lot of groups and things that we'll test, because by hand it's quite impractical. But I want to be aware of problems that could arise, sort of limitations of these methods, and an alternative. So that hopefully gives you a good basic idea of ANOVA, and then we can build on that with some specific examples for you to see all the details slowly, getting you to the point where you can hopefully do it as well. All right, until next time.